When in elementary physics you first start learning about the forces that act on an object or a load, it seems that one of the biggest challenges is to try to identify those forces and then to draw vectors that represent them. And the challenge doesn't stop there because the problem becomes even more complex. Sometimes the load is on an inclined plane at a certain angle, and you need not only to identify all the forces acting on it, but also to use the appropriate formulas to calculate these forces. Isn't this a typical scenario? Your teacher presents a word problem, goes to the board, draws arrows calling them vectors, points to an angle which is in a different location to the angle which you thought was theta, and then uses trigonometry to solve for the magnitude of the force in question. What adds to the confusion is that the arrows are not always drawn with consistency. Sometimes the same force would be shown as pointing up, and sometimes it's pointing down. Sometimes the arrows originate from the center point of gravity of the load, sometimes from the top of the load, and sometimes from the bottom of the incline. At this point, you are not aware that there are actually several ways of representing the information you are trying to decipher. In this video, I will show you a variety of ways where, through vectors, you can understand the forces at play. Using the laws of similar triangles, I will show you the various angles that will be equal to the angle of the incline and the different ways of calculating the forces in question. One of the major forces acting on an object is the gravitational force. A helpful way to try to understand this force is to imagine the object sitting on a scale. The weight given by the scale corresponds to the effect that the gravitational field intensity at that certain location has on the mass of the object. This effect is represented by an arrow, a vector, that is drawn perpendicular to the surface. Conventionally, the vector initiates from the center of the object's mass and heads downwards to the center of gravity of the surface on which the object is resting. The pull downwards by the surface, i.e., the gravitational force, is equal to the weight of the object. But not all drawings are guided by convention, and one can as easily find a gravitational force vector that starts at the bottom of a surface. Opposing the gravitational force is another force that pushes upwards from the surface on which the object is resting. This force, called the normal force, is also a force perpendicular to the surface. Note that on an inclined plane, the normal force is perpendicular to the incline. The vector representing the normal force can also be transposed downwards. Represented this way, one can easily see that on a horizontal surface, the normal force is equal to the gravitational force. Other forces act on the object in a direction parallel to the surface. A push or a pull applied on the object is logically called the applied force. Opposing it is another surface force, that of friction. It stands to reason that when these two parallel forces are equal, in other words, when the applied force is equal to the friction force, the two, being opposite forces, cancel each other and the net parallel force will be zero. There is zero acceleration. The object will be at rest or will move at constant velocity. Similarly for the perpendicular forces. When the gravitational force is equal to the normal force, the two cancel each other and the net perpendicular force is zero. There is no movement in the y direction. But all this discussion is merely an introduction to the more complex topic of a load sitting on an inclined plane. In this graphical image, we can follow the relationship among three forces: the gravitational force, the normal force, and the parallel force. The parallel force is essentially the combined effect of the applied force and the contact friction force. The contact friction force acting between the upper surface of the plane and the bottom surface of the object holds the object in place and provides resistance to the external applied force placed on the object to move it. Note that as the incline becomes steeper, the effect of the normal force, represented by the blue vector, is diminishing, and the effect of the force parallel to the incline, represented by the green vector, is increasing. It is important to keep in mind that all this while the gravitational force, represented by the red vector, remains constant, as neither the mass of the object nor the intensity of the gravitational field is changing. An important question comes to mind as we watch the incline become steeper and steeper. What is it that initially keeps the object stationary, and at what point will it slide down the plane? What initially keeps the object stationary is the friction force. When the applied force exceeds the friction force, the object begins to move and to accelerate, and the resulting force is referred to as the parallel force, the force parallel to the direction of motion. Another name for the parallel force is effective force. A typical question you might encounter would be one in which you are asked to calculate the magnitude of various forces acting on a load that is sitting on an inclined plane at a certain angle theta. In elementary types of such questions, you would be told that the friction force can be ignored or that it is equal to zero. So, let's set off to examine the various forces by first drawing vectors to represent them. Remember, the normal force will be represented by a vector pointing upwards and perpendicular to the incline. The gravitational force will be represented by a vector pointing downwards and perpendicular to the horizontal surface, and the parallel force, or the effective force, will be represented by a vector that is parallel to the incline and showing the direction of movement. Now, one's initial instinct is to focus on the right triangle highlighted in green and to start calculations. And though this is not the way to proceed, it does give a starting point for angle measurements. Based on the angle theta and the right angle, we conclude that the third angle will be equal to 90 degrees minus theta. However, we note that this green triangle does not include all the forces acting on the load. And key to solving such problems is to work with right triangles in which each of the three sides represents a force acting on the load. Our green triangle includes the parallel force, it includes the gravitational force, but it does not include the normal force, F of n. We get around that by transposing the vector that represents F of n and shifting down the vector representing the parallel force. And here we have a right triangle whose three sides represent the three forces at play on our load. Calculating the angles of this triangle is straightforward and can be done in various ways using the laws of geometry, similar triangles, and parallel lines. Let's start by drawing a line over the base vector and another line parallel to it at the vertex. Then, withdraw a transversal line as an extension of the normal force vector. Recall that the normal force is defined as a force perpendicular to the incline, giving us an alternate interior angle that is also 90 degrees. This establishes the yellow triangle as a right triangle. Let's draw a transversal line as an extension of the gravitational force vector and focus on another pair of alternate interior angles. One of these was already calculated to measure 90 degrees minus theta, giving that same value to the other. We are now left with the last angle of the triangle. Because the sum of the three angles of a triangle is 180 degrees, we conclude that the last angle must be equal to theta. Finally, we note that this is the same measurement as the angle of the incline. Now that the right angle and the angle theta have been identified, we can use trigonometry to calculate the magnitude of the vectors. That is, we can calculate the length of the sides. Since here we are dealing with angles of right triangles, the ever-memorable mnemonic SOHCAHTOA can come into action once we relabel the force vectors. The gravitational force vector Fg is the side opposite the right angle and also the longest side. Fg is the hypotenuse of the right triangle. The other two sides will be labeled according to their position relative to the angle theta. The parallel force vector is the side opposite to the angle theta. Recall that sometimes the parallel force is called the effective force. Finally, the normal force vector is the side adjacent to theta. Applying our memorized formulas, we can manipulate the variables to solve for the unknown forces and/or the angle of the incline. I started this video by saying that what makes such problems confusing for the beginner student is the fact that the positions of the force vectors are not always drawn with consistency. But all you need to remember is that force vectors can be drawn anywhere, as long as they are parallel to their original positions. In the example I just worked through, our right triangle was drawn in this position. In the following examples, I will set up right triangles in other positions and show you how to analyze them from different perspectives. I will also set up the necessary steps to structure the process. Step 1 is to determine the force vectors acting on the load. Step 2 is to shift vectors parallel to their original positions in order to create a triangle bounded by the three forces. This will always be a right triangle. I like to work with a triangle that touches the incline. Actually, it can be drawn absolutely anywhere. It can even be drawn upside down. But for now, we'll work with this configuration and in this position. However, do remember that any configuration will work as long as the gravitational force vector is drawn perpendicular to the horizontal surface, the normal force vector is drawn perpendicular to the incline, and the parallel force vector is drawn parallel to the incline, that is, parallel to the direction of movement. Step 3 is to identify the right angle and the angle theta. The right angle is easy to spot due to the definition of normal force as the force perpendicular to the incline. Identifying the angle theta requires further application of geometry rules. We start by marking off the angle of the incline as theta. We extend the gravitational force vector and mark the vertex as a right angle. This creates a triangle whose third angle is equal to 90 degrees minus theta. The angle opposite will also be 90 degrees minus theta, making the third angle equal to theta. This is equal in measurement to the angle of the incline. In step 4, we identify the hypotenuse, the opposite side, and the adjacent side. This final step guides us on which of the 3 formulas we need to use in order to apply our trigonometric ratios. Let's practice finding theta and identifying the sides using other configurations. Following steps 1 and 2, we can end up with a right triangle in this position. As I said earlier, I find it easier to work on a triangle that touches the incline. Now, I will shift it away from the clutter to give me better focus. In step 3, we identify the angle theta. We have thus used geometry arguments to prove that this is our angle theta. In step 4, we identify the sides. This is the hypotenuse, this is the opposite side, and this is the adjacent side of a right triangle. Now, we can calculate the angles and/or any of the sides. Let's work on a final example. We will complete steps 1 and 2, and this time we will place our right triangle in this position. In step 3, we use geometry to determine which angle is theta. And this is the angle theta, which is equal to the angle of the incline. In step 4, we identify the sides. And to do our calculations, we use trigonometric ratios. By now you may have figured out the pattern. No matter where we place the right triangle of interest or what our configuration is, the gravitational force on the load will always be represented by the hypotenuse. The parallel or effective force will always be represented by the opposite side, and the normal force will always be represented by the adjacent side. To apply what we've just learned, let's start with the following word problem. A 5-kilogram box is sitting on an inclined plane at an angle of 40 degrees with the horizontal. Calculate the magnitude of the 3 forces acting on it. Step 1. Determine the force vectors. Step 2. Draw a triangle bounded by the 3 force vectors. Remember that you can draw this just anywhere. Step 3. Identify the right angle and the angle theta. As a shortcut, you may recall that theta is the angle opposite to the parallel force vector. And here is the geometry proof. Step 4. Identify the sides. As with any word problem, we start our solution with a list of what's given and what we are looking for. Let's first solve for FG. Recall that the gravitational force on an object is its weight, W, which can be calculated by multiplying its mass, m, by the gravitational field intensity, G. On Earth, the gravitational field intensity is equal to 9.8 newtons per kilogram, giving a magnitude of 49 newtons for Fg. Next, we'll solve for Fn. Fn, being the adjacent side in our right triangle, is equal to the cosine of theta multiplied by Fg, the hypotenuse. Plugging in and solving gives Fn is equal to 37.5 newtons. Similarly, we can solve for the parallel force. Though either one of these two formulas can be used to solve for the parallel force, we'll use the first one. F parallel is equal to sine theta times Fg, obtaining 31.5 newtons for the parallel force. Here are the measurements of all three sides. What's interesting is that because we already had the measurements of two of the sides of the right triangle, we could have just as easily used the Pythagorean theorem to calculate the magnitude of the third force. Let's add another challenge to our problem and calculate the acceleration of the box along the incline. The assumption that there is no force of friction acting on the box simplifies the problem. We start the solution by listing what we're given and what we are looking for. Using the fundamental relationship force is equal to mass times acceleration, noting that the particular force in question is the parallel force, we rewrite the formula to solve for acceleration. Writing our units as newtons per kilogram, though essentially correct, does not accurately describe units of acceleration. The basic formula, F is equal to m times a, itself can help us figure out alternative units. If force is measured in newtons, mass in kilograms, and acceleration in meters per second squared, then we conclude that 1 newton is equal to 1 kilogram meter per second squared. Through substitution and cancellation, we end up with more conventional units. The acceleration of the 5 kilogram box along the 40-degree incline is 6.3 meters per second squared. Let's continue using this same concept in other situations. Here is a typical problem. What is the effective force on this 45 kilogram skier as he slides down the 30-degree angle hill? To solve, we follow the previous outlined steps. Step 1. Determine the force vectors. We draw the normal force vector, the gravitational force vector, and the parallel force vector. Step 2. Draw a triangle bounded by the three force vectors. To do this, we shift the normal force vector to get our right triangle. Step 3. Identify the right angle and the angle theta. We can prove through geometry arguments that this is the right angle and this is the angle theta. Step 4. Identify the sides. This is the hypotenuse, this is the adjacent side, and this is the opposite side. We start the solution by listing the given information and the variable we are looking for. In this case, it's the effective force. But do recall that the effective force is also sometimes referred to as the parallel force. So in our diagram of the right triangle, we are looking for the opposite side. The trigonometric ratio for solving for the opposite side is sine theta is equal to opposite over hypotenuse. We substitute F effective for opposite and Fg for hypotenuse. Also recall that gravitational force is also referred to as weight, which can be calculated by multiplying mass by the gravitational field intensity. Further substitution gives sine theta is equal to effective force divided by mass times the gravitational field intensity. Next, we isolate the unknown variable and solve. The effective force is 220.5 newtons. Other questions may be more challenging. For example, you may be asked to find the angle theta. Here's an example. Calculate the angle of the hill if the 45-kilogram skier is sliding down at an acceleration of 3.6 meters per second squared. We start off by drawing the right triangle bounded by the three force vectors and setting up the solution by listing what's given and what we are looking for. Note that what we are looking for is the angle theta, which means that we need to perform some clever manipulations and substitutions in the formulas we know. Let's list the formulas at our disposal. Because we have mass and acceleration, we can start off by solving for force. Specifically, we need to solve for effective force, which is the force parallel to the direction of movement. Plugging in, we calculate that the effective force is equal to 162 newtons. But our goal is to find the angle theta. Here we can use our trigonometric ratio. Sine theta is equal to opposite over hypotenuse. Then substitute F effective for opposite and Fg for hypotenuse. Further substituting and plugging in gives sine theta is equal to 0.367. But let's remind ourselves that what we are looking for is theta, not sine theta. For this, we must use the following relationship. If sine theta is equal to opposite over hypotenuse, then theta is equal to inverse sine or sine to the minus 1 of opposite over hypotenuse. Sine to the minus 1 is also known as arc sine. So, theta is equal to sine to the minus 1 of 0.367, which is actually better expressed as arc sine 0.367. To do this calculation, we need to ensure that our scientific calculator is set to the degree mode. To get the sine to the minus 1 function, we click on inverse sine and punch the numbers 0.367. The answer is 21.5 degrees. A more sophisticated way of solving the problem is by doing all the mathematical manipulations and substitutions at the beginning. Note that in this situation, it is better to regard g as acceleration due to gravity and to use the units meters per second squared as opposed to newtons per kilogram, which is the conventional unit for gravitational field intensity. Whether it's newtons per kilogram or meters per second squared, the value for G on Earth is constant at 9.8. Check out this technique and see if you prefer it. You might, as I do, find its elegance highly satisfying. Thank you for watching. I hope this video was helpful.